Hey guys, so today I wanted to talk about this. This is a project that ultimately ended up becoming part of a bigger project later on down the line because I needed liquid nitrogen or liquid air really to cool down a cryo trap. So this is a project that Ben Krasnow on Applied Science did originally. His was a lot more complicated though, had a lot more bells and whistles. This is just a much simpler version, and today I'm going to talk about it, and I'm going to talk about how I did it, all the methods I used, where I got my parts, and all the problems you'll probably run into if you try and do this project. Now, since this is a liquid nitrogen machine, the heart of the project is this. This is called a Stirling type cryo cooler. It's this long cylindrical thing. It's sitting inside this sort of case right here. This is just to help direct airflow from this fin you can see right here to the top. So it'll pull air in that way and exhaust it out the top here to keep it cold. Now, to build this, normally this is built into a big case, so airflow isn't a problem, and the case is actually what helps the air move through this fin here. But to build this, what I did was I actually just went and I got some plumbing fittings. These are for like a sewage lines. Like this is I think a 3-inch to a 4-inch. This is just some like soft. It's not PVC. It's like corrugated PVC almost. It's really easy to cut, which is why I chose it. And then this is just a connector so that I could put like a 12-volt brushless DC fan on there to help the air move through. So I'll try and throw a picture up on the screen here in a minute. But the reason I chose this kind of soft PVC is because you'll notice if this were all apart, there's these little tabs on the cryo cooler itself, which make it just slightly larger than the 4-inch diameter that this is, so you can actually cut grooves in this, or slots, so that'll slip in there nice and give you a good fit. Now, obtaining this thing, as it turned out, was not the easiest thing in the world because the units they come out of don't generally come up on eBay too often for resale. I actually had to wait about a month before some company in Florida underwent liquidation, and they sold off a huge stock of these. And they're still really expensive. I had to pick mine up for like $698, I think the final price was. So yeah, they're pretty punny, but in my opinion, they're definitely worth it for what they are. The alternative to this is to use something like this. Now, this is a full-size cryo cooler. I mean, this thing is huge. The other cryo cooler is actually all self-contained. The helium's there. Everything you need to make the cryo cooler work is there. You just plug it in and it goes. This is a little bit different. These two lines here are actually to circulate helium through it. All the helium does in here is it gets hot. Now, once the helium is hot, it actually gets sent to a different unit which cools it down, which is where these two hoses lead off to. And also, this thing's pretty heavy. I'll try and put an exact weight up, but it feels like it's about, 30-40 pounds. It's definitely not something you could balance on top of a thermos like you can with this smaller cryo cooler. The one advantage to this is that these, you can find them on eBay all the time. They're constantly there. But again, another disadvantage is that I actually had to modify this one. The inside of it, which I'll show you in a second, this inside part here, which actually, it had a big baffle in it that had to be removed. Now, generally, in the industry, these things are used to act as cold traps. What they do is you put them on a high vacuum system, and they'll freeze any contaminants you have in the system, and they'll condense them so you can get a lower ultimate pressure. Now, this is the main board to run the smaller cryo cooler here. All it does is it takes anywhere from 20 to 30 volts in. I'd recommend at least 24 volts, or it'll actually start throttling you at around 150 watts. It won't go over about 148. So it takes 20-30 volts in, and it turns it into a 12-volt AC sine wave that comes out over here to power the cryo cooler. Now, the one problem with this board is that it won't normally work. Like, you can't just take the whole thing apart, plug everything back in with all the physical components separated and expect it to work, because what it's doing is it's actually looking for the temperature in this component. It's looking for this component to start decreasing in temperature, and as this gets colder, it'll ramp up the power on the Stirling cryo cooler. Now, to get around that, what you have to do is you have to go through the software. You have to find the software for this particular model, which you can, I've noticed, usually whoever's reselling these will send you that software for free. But you have to find that software, and then you actually have to go into the software and change the firmware settings to make this manually run at whatever power you want it to run at. And one thing I do want to say about that is this. You have to ramp up the power really slowly on these things. Like, you can't just start the cryo cooler running at 150 watts. It'll kill the cryo cooler. It needs to, if you just set it to 150 in the software, it'll ramp up a little faster than it's supposed to, which is why I'll usually go like 3 settings, like, 50, 75, 100, and then 150 to give it enough time to cool down. And the major problem though is you can't turn this off and then restart it and then just expect it to ramp up again. It'll actually start the cryo cooler while it's warm at 150 watts, which is really bad for it. It will kill it. So before you shut this down, you have to make sure to set it back to like 10 watts is the starting power. And once you set it back to that, it'll come on just fine once you switch it back on. Now, if you're wondering why this is, why I couldn't replace this like Ben Krasnow did in his video, he actually, he replaced this entire assembly with 2 resistors just to fake this board working. The reason I couldn't do that is, one, I don't have 18 ohm resistors. I couldn't be bothered to find them, and I really don't care also because I'm eventually going to end up installing this in an X-ray spectroscopy unit. So this being there is really fine. It's not going to matter. One thing I do want to mention about this board is that when you originally find it in the case, it is riveted in there. The only way to get it out is you're going to have to go in there with a drill. Well, first you're going to have to remove the board from the metal backplane that it sits on, and you're going to have to drill each individual rivet. Now, one of the major problems I had with this design is balance. Normally the way I do this, and I'll put a picture up on the screen in a second, is I put this with half of a 3D printer reel on top of a thermos. And it just all kind of balances on top of the thermos. And that can go really bad because when you're turning this off, maybe you knock it over, all your liquid nitrogen's gone. So that's probably one of the biggest design flaws, and I'm eventually going to mount this in sort of a stand so that you will move the dewar with respect to it rather than it moving with respect to the dewar. And so I'll eventually just get, like a laboratory jack and use that to raise the dewar up to the cold head part of the device here. Another major issue I had with this was this is made of rubber, and this gets hot. And if you know what hot rubber smells like, you wouldn't want that to happen. After about a week of continual use, the smell kind of went away, and it's been getting weaker and weaker ever since. So I'm not sure quite what's going on, but just know that if you use rubber, it will smell for at least the first week. And the next thing I'm going to do is I'm going to set this all up. I'm going to let it run for about 8 hours, and we're going to see what we get. Now I should mention that to power this I'm using just one of these standard cheap Chinese power supplies. This one's a 24 volt. And so far they've actually worked pretty well. I don't see any voltage drop as the current goes up. And they also have the automatic fan, so it's only on when this is actually drawing a significant amount of current. One problem I did forget to mention is the vibrations. If there's no paper towel here or there's nothing to damp the motion of this. Now there's already a spring in here, as you saw in Ben Krasnow's video. He showed it. He used like a slowed down shutter so you could really see that effect. But if there's nothing here to damp the vibrations of this, it'll actually shake the floor. If it's on like the second floor of a building and you're under, you can actually hear it shaking at 60 hertz. Now to find the password in the software, I actually had to do a little bit of digging. What I did is I decompiled the code, and then I just did a Control F for the word password, and it's all in Java, so you can easily decompile it. And in one of the jar files, it found the setting for the password. My password happened to be the word tacit in all capital letters. I don't know if it's the same for all units. You can try it, but you do need the password to set the power that the cooler runs at, or else if you don't know the password, the maximum power that the cooler runs at is about, I think, 30 watts, which really isn't enough. It needs to be closer to 150 if you want to get any kind of reasonable amount of liquid nitrogen. Now, one thing I forgot to mention is just the general noise. This thing does get pretty noisy, especially at full power, so I wouldn't recommend running it in the same room that you are. I don't know if you can hear that. It's not quite so noisy right now because it's only running at about 61 watts, but it does get there. Alright, so now it's running at just about full power, so I'll see you in 8 hours. Alright, so now it's the morning and I'm going to take this whole set apart and we're going to see what we got. Now to be fair, this isn't pure liquid nitrogen. Since I don't have a nitrogen purification apparatus like Ben Krasnow did, this is about 20% liquid oxygen, and I'm going to show that by using this magnet. Oxygen is diamagnetic, so it'll stick to the magnet. See, I'm not touching the liquid, but there we go. That's it for today. In my next video I'm going to talk about another project I did, which this was the project that became a part of that one. So stick around and thanks for watching.